Hi there. Welcome to the session Similarity Analysis of Global Chemical Product Labels. My name is Thomas and I'm Senior Data Science Consulting at Woodmark. And in this session, I want to demonstrate you an NLP approach to protect environment and health. So let's have a look at the agenda, what awaits us for the next 20 minutes. And we first talk about the motivation. Why are we doing this? What are pesticides? How can we solve some problems with the help of similarity analysis? What are chemical product labels and how they look like? And the main part of this session is about how to solve this problem, and this ends with some further ideas and suggestions. So for the beginning, let's start some facts. The amount of pesticides used worldwide has increased by 80% since 1990. In some regions, such as South Africa, it has increased by almost 150%. There are approximately 255 million pesticide poisoning incidents per year in Asia, just over 100 million in Africa, and about 1.6 million in Europe. So as you see, that are very hard facts, and there are a lot of disadvantages and deep impact on our environment and health by the usage of pesticides. It can lead to the reduction of biodiversity. It can cause pollution of groundwater and soil, and also contaminate food products. And all these things can have direct or indirect impact effects to acute poisoning and chronic diseases or environment-related health problems. So this pesticides, the chemical labels, product labels, can be divided in three kinds of pesticides, like herbicide, fungicide, and insecticide. And I want to give you an overview how to distinguish them, because it's important for the later analysis what we can do with the results of this. So herbicides are used to kill or inhibit the growth of unwanted plants, such as weeds. And fungicides can inhibit the growth of fungi or the spores, and insecticides for insects. Yeah? And the environmental impacts for those kinds are also different, but in some ways similar. They can affect the diversity and abundance of wild plant, can damage crops, and contaminate food products with residues, can affect balance of microorganisms, kill beneficial fungi that helps plant to grow or decompose organic matter, can kill beneficial insects that pollinate plants or control pests, also harm other animals that feeds insects, and so on. So the list is very long, just to name a few. Yeah. And the impact on our health, let's say, can be linked to cancer and other health problems in humans and in animals, can cause respiratory problems or skin irritation, can cause neurological damage, or even death. So the question is, okay, after knowing all these hard facts about pesticides, what is the link to similarity analysis here? How we can solve some problems or reduce the use of pesticides, so we can hopefully after that identify alternative plant protection products that are less harmful to the environment or health by considering the toxicity, the persistence, or bioaccumulation of the active ingredients. It helps us to reduce the use of pesticides or replace them with more and then environmentally friendly alternatives. This will protect both biodiversity and human health, support the direct use by consumers with highlighted risk and instructions of usage. And it is a very good and wonderful basis for further analysis and use cases with data science techniques beyond chemical product labels. So before starting with a walk around or workflow of our analysis, let's have a look. How does such a chemical product label look like? What are the content of such a label? And, here are some snippets from the label, some screenshots, and they are stored in many pages of PDF documents, and they all have some similar style. It's like they have upper letter phrases like keep out of reach of children, caution, user safety recommendations, first aid, precautionary statements, or direction for use. And our goal is to extract all these phrases, store them, analyze them, and compare on basis of these phrases the similarity of those product labels. We can do it in the following way. So this is a Python open source framework. All tools and frameworks used here can be done with Python. Yeah? First, starting with tokenizing and with the method parsing and some regex, then go on with vectorizing using the model word2vec, reduce the dimensionality of this data with TSNE, and in the end, before visualizing the labels, some clustering with evaluating by the red score and cosine similarity. So these are the 4 main steps to find a solution for such a problem. And just one approach. And let's start with the first one. Let's make these product labels usable. And in NLP, tokenizing stands for breaking down text in smaller units as phrases like we have seen the direction of use, or on the right side, upper right side, you'd see the snippet user safety recommendation, or engineering control statements, environmental hazards. You know? We can do some text extraction of the documents as PDFs by parsing methods and use tools like Tika or PyPDF2 from Python, and we can pre-process this plain text by removing digits, display special characters, strip tokens, and so on, getting upper capital letters, remove processes with regex, and in the end, we want to join all these phrases, upper letter cases phrases, into maybe a pandas data frame you see on the bottom right. Yeah, you see for every row you see a list of the collected phrases stored here, ordered by country, here in this case, beginning with Australia. So after we make the data usable, we want to transform this data, this text, into numbers to apply some mathematical and data science techniques on it. So we call it vectorizing, and it's the process of converting text data into numerical vectors. Yeah, so we're turning lists of phrases to lists of numerical vectors. And for this, we're using the word2vec model from Gensum. Word2vec is a pre-trained neural network that can learn word association from text. It can produce word embeddings in form of vector representations for their similarities. And in the end, we get an output like this NumPy array with a dimension of 100 for each row in our data frame. So for each label, product label, we get a vector with a dimension of 100 expressed in numbers and floats in this case. So as you can see, we have a very big dimension for each product label. So for visualization purposes and clustering, it would be better just to reduce this. Yeah. So we're going to a dimensionality reduction. We make them smaller. The process of reducing the number of features or dimensions, in this case, that represent text data, here our labels, in numerical vectors. And I found an approach to to use the technique TSNE, T-distributed stochastic embedding from sklearn. It's a nonlinear technique that is well suited for high-dimensional data to lower-dimensional data, so maybe 2 dimensions in this case, but also for 3 dimension. And it's great for visualizing cluster data and to compute the similarities between data points, and they are converted into probabilities and to minimize the difference between the probabilities in the high dimensional space and the low dimensional space. So as you can see on the right side, we're going on with a NumPy array for each row, for each label with a dimension of 100, and reduce them to a dimension of 2 for each label. In the end, we want to make them exclusive. So we want to put every data point, every label into one clusters where they are maximal similar to each other. So this clustering in NLP is a process of grouping similar texts or sentences, in this case phrases, based on their content or meaning. Here it's low dimensional vectors of phrases. The method I use was k-means from scikit-learn, sklearn, and it's an you already know, unsupervised machine learning algorithm that partitions a set of text into k predefined clusters. I also used the silhouette score from sklearn to measure similarity of product labels within the clusters. It's not also for measuring the similarities, also for evaluating the clustering itself. Yeah, so when we build a pipeline over n iterations of clustering, we can also run parallel or within it a pipeline to evaluate the performance of the clustering. So we can measure the similarity of the label within a cluster, but we can also measure the similarity of the clusters itself, so between the clusters. Yeah? And you can do this with the cosine similarity or 1 minus cosine distance. Yeah? In the end, you can loop over n clustering iterations to find the optimal number of clusters k for a global maximum silhouette score. And in the upper right, you see a screenshot from an output I computed just for number of cluster of 5. And in the end, I got the best result was an overall silhouette score of 0.5. And the best you can get is 1. The minimum is -1. And you see for every cluster, the average silhouette score, the size of the cluster, so how many labels are inside the cluster, and the minimum score and the maximum score containing it. And when you have a deeper look or more detailed look to the first clusters, cluster 4 and cluster 3, which have a size of 16 and 20, you can see they have a very, very high silhouette score. That means inside the clusters, they are very similar. So there might be 16 product labels which are very similar to each other, even if they are different products. And this also goes for cluster 3. That is what the silhouette score is giving us back. And yeah, we can also measure the distance between those clusters. You can figure out the highest similarity between cluster 0 and cluster 2, and cluster 0 has an average silhouette score of 0.42, and cluster 2 0.545. So, but the question is, okay, they have a very low silhouette score inside, but the cluster itself are very similar to each other. What is the reason of it? And I think it can be that both are very chaotic, or there's a lot of chaos inside each cluster, and cluster 0 is somehow almost chaotic like cluster 2. So it's like how you can interpret it. Yeah. And in the end, we want to visualize our clusters. So we have our 5 optimized clusters for this case. And visualization in NLP is a process of creating graphical representations of text data or models to facilitate understanding, exploration, and communication. And the type I used here was just to scatter them with Plotly and do an interactive plotting to identify similarity or dissimilarity of product labels clustered for specified categories as countries, continents, type of pesticide, and so on. So, and this analysis and this visualization in the end can often be a very good inspiration for further ideas and analysis. And if you would zoom in, we could see in the down left, for the country USA, you see some 2 colored clusters, the green one and the orange one, and that are exactly the 2 clusters we saw a slide back. The silhouette score was highest, so they are very decomposed, so very close each point and very far away from other clusters. So, but if you would raise the number of clusters or pipeline, would get the best overall silhouette score, then it would be creating just maybe some more clusters. At the 2 red clouds in the middle on the left side, there might be also some 2 different clusters. So, and we can do it for countries, we can do it for continents, and also analyze the phrases, similar phrases inside the labels. And this give us somehow an idea, okay, what can we do with such results in the end? So what we have seen here is a data science approach. It's not AI. But the good thing is now we can put AI on the top of this result. We can use OCR to get some specific text extraction. We can build up a recommendation engine for consumers with interactive dashboards. We can create a guide for the selection and use of pesticides. We can create new product labels with the help of LLMs. We can create new warning labels, identify regions which pesticides are in particularly high demand. We can even precise distinction of products with significant degree of harm. So what I want to say is here, you have to be very careful if you have such a project, if you use general data science techniques or just directly start with LLMs. And LLMs have also some disadvantages. They are very costly in computing power and energy, and sometimes are not very accurate. So if you are capable of and have the skills and very clear defined steps to solve your problem, always try to find a solution with general data science techniques and then put LLMs or other AI approaches on top of it. Thank you very much. And if you have more questions, some suggestions, or just want to get in touch with me, reach out via LinkedIn. And thank you. Bye.